let's move. The maintenance of the population is critical to determine the cell size. Cell defect, for example, in the P50 system, when they detected the DNA damage, it starts to oscillate if we measure the concentration of P53 level. So depending on whether this oscillation is sustained or not, their rate become completely different. For example, you can die, the apoptosis, or you can stop the cell cycle arrest. So they can determine to repair the DNA damage. However, this oscillation is regulated by very noisy biochemical reactions. For example, when DNA damage is detected, the MDM2 releases the P53 protein. Then it promotes transcription of MDM2, and it again represses P53. By forming this negative feedback loop, they can generate the rhythms. However, as you can see, there are too many biochemical reactions. For example, the binding between the P53 and MDM2, or the degradation of P53 or MDM2, or transcription of MDM2. So, they are regulated by very noisy biochemical reactions. So it is hard to sustain the robust oscillation. So, the question raised by this paper is that how long-term oscillations overcome this biochemical noise to maintain its oscillatory dynamics. So they measure the concentration, measure the concentration of P53 and MDM2 by fluorescence protein. The blue one is the P53 and orange one is the MDM2. So if we measure their concentration over time, we can, after damage, we can detect, we can observe the oscillatory dynamics as time goes. But interesting is that, so we can measure the time-dependent period of P53. Then, if we measure, then as we can see, their period is robustly maintained over time with about 4.6. However, interesting is that if we measure the period of MDM2 over time, it shows some transition to another period. So if we draw the period as time goes, it shows the bimodality. The one period is similar to that of the P53, but the other period is twice of the P53's period. Then the natural question is that what happened during MDM2 period transitions? So to see what happened during the MDM2 period transition, they magnify this part, show the transition. This is that graph. And then, as you can see, as I stated, when P53 increase in this region, even the P53 increase, the MDM2 decrease. This is unnatural because due to the negative feedback, P53 promotes the transcription of MDM2. So when P53 increase, MDM2 should increase. But in this period transition region, they show some insensitivity to P53 induction. So we will call this phenomenon, we will refer this phenomenon to as the pulse skipping. So, and then if we should draw the phase plane of the P53 and MDM2 during the oscillation, during their trajectory is completely different during the oscillation and during the pulse skipping. So question is that so this is not the restricted to this one set. They measure the period over the about the 400 cells at the various time point. So in this graph, the x-axis is the P53 period and y-axis is the MDM2 period. As you can see, most of cells follows the one-to-one ratio line, but some part of point they show the 2:1 ratio. Yeah, follows the line with the tiltation of 2. It means that periodically is widely occurred. So MDM2 pulse skipping is general phenomenon across the cell population. So to see what happened in the during the pulse skipping, they align the two cases. The solid line is the pulse skipping cases, and dashed line is the normally oscillating cases. They aligned these two, and they compare their amplitude. Then, as we can see, during the oscillation and pulse skipping, their amplitude is similar. But before the pulse skipping, in the pre-skip pulse, the pulse skipping case shows the higher amplitude. Sorry, similar amplitude, but if we see the concentration of MDM2, it shows a clearly significantly higher amplitude in the pre-skip pulse. And this MDM2 pulse skipping event is mostly occur randomly. So this is the distribution of a cycle where the pulse skipping occurs. Except for the second cycle, they show the nearly uniform distribution. It randomly occurs. Then recall the elementary statistical class. Then some event occurs at the same rate every time. During some time, the number of the event, the number where the events occur, follows Poisson distribution. Yeah, so if we measure the pulse skipping, number of pulse skip, then it follows the Poisson distribution. And what is the time difference between the event following the Poisson distribution? It is the exponential distribution. So when they measure the intervals between skips, pulse skipping, it follows the exponential distribution. So this experimental data supports that MDM2 pulse skipping event mostly occurs randomly at a constant rate. So we can conclude that this pulse skipping is really mainly driven by the biochemical noise. Then the question is what is the potential mechanism by which MDM2 pulse skipping occurs? So they propose based on the negative feedback mechanism. So there are several mechanisms where MDM2 repress the P53. The first one is that MDM2 can destabilize P53 through the ubiquitination or increasing decay rate. The second one is that MDM2 can form a complex with a P53 not to promote transcription of MDM2. So there are two mechanisms where MDM2 suppress P53 transcription. So they hypothesized that this higher level of MDM2 enables the transient formation of a higher level of MDM2 P53 complex leading to the MDM2 first skipping. Imagine that in the pre-skip burst, the concentration of MDM2 become higher. Then naturally the complex of MDM2 and P53 also become higher. Then inhibition by MDM2 by the second mechanism also become stronger than the PO13 level decrease. Then due to the repression of its transcription, the MDM2 level is decreased. Then it can lead to the first skipping, because during the first skipping, MDM2 does not increase. So to test this hypothesis, they measured the transcription level. So red one is added, the red one is the mRNA level. So with the red one, we can, but they use the gray color in the plot. This is the mRNA level, MDM2 mRNA level. So this is transcription. So as we can see, during the first skipping, the transcription of MDM2 is greatly compromised. So transcription is repressed as they hypothesized. Then the natural question is that, is it really caused from the increased P53 MDM2 complex? This is indirect evidence. So they checked whether it caused from the P53 and MDM2 complex. So to test this, they added some component, Nuclein 3. The Nuclein 3 blocks the interaction between P53 and MDM2, so they cannot form a complex. So this is the control case. There is no Nuclein 3. So in the second case, they applied the Nuclein 3 to the cycle of the rising page of P53. Then, because P53 and MDM2 cannot form a complex, the level of P53 increase, and as the P50 increase, the MDM2 level also increase. And this increased MDM2 level caused the first skipping. And then they apply the Nuclein 3 again during both of P53 and MDM2 increase. Because during this time, they cannot form a complex, first skipping is abolished by the second Nuclein A application. So by the first application, first phase treatment of Nuclein 3, they induce the first skipping, but by blocking the formation of P53 and MDM2 complex in the second Nuclein 3 complex treatment, they abolish the first skipping.
How they measure the percentage of first skipping?
So they tested it very many times and then counted.
So
You can get a percentage. How frequently it occurs? How frequently first skipping occurs in the multiple experiments? So they conclude that MDM2 first skipping can be caused by the suppression of MDM2 transcription via the P53 MDM2 inhibitory complex. But the problem is that, so then during the first skipping, NDM2 level is very low. But P53 shows the sustained oscillation, even some repression by NDM2 disappear. Then we can hypothesize that there might be some buffering mechanism during the NDM2 first skipping, even the NDM2 level is low. So we propose allelic buffering models. The allelic buffering model is that they hypothesize that some allele can the buffer the effect of the other alleles of mismatch. Allele is the 대립유전자 in Korean. So they have a chemo with allele A and allele B. So during allele A experiencing the NDM2 pulse skipping, allele B can repress P53 with another mechanism. So during the NDM2 pulse skipping over one allele, the remaining alleles can contribute to the production of NDM2 following the P53 degradation. So another repression buffering mechanism. So to test this, they developed an NDM2 dual allele reporter cell lines. So they can detect also allele A, allele B's production. But the difference is that for the allele A, they can only measure the transcription level. But in the B, they can only measure the MDM2 level. So they can measure the both alleles the production, but one is the transcription level, one is the MDM2 level. That's the difference. So we have a two allele. We have two DNA, so there can be a four scenario. First one is that no skipping in the both allele. And second scenario is the pulse skipping in the allele A. So no transcription. And third scenario is that only pulse skipping in the allele B. They shows the decrease of MDM2. And the fourth scenario is that the pulse skipping for both allele. So there are four cases. We can observe the four cases. But when only after both skipping, if we measure the amplitude of all rhythms, the subsequent post-skip P53 amplitude is significantly higher only after both skipping. It implies that transient weakening of allelic buffering. So what is the key of this allelic buffering model? During one allele is experiencing the pulse skipping, the remaining allele have a role instead of the getting some pulse skipping. But in the scenario for both of allele are experiencing pulse skipping. So the other one cannot support one cannot support the other one. So it shows the increase of the amplitude only in the both skipping. So we can conclude that with this data, allelic buffering during ambient pulse skipping exists and functions in maintaining P53 amplitude during the oscillations. So to see how they affect the amplitude of oscillations, they developed mathematical model to describing this two allele dual allele system. They described the model with the OD in the paper, but they performed the stochastic simulation. So just to see the equations or understanding. So let's see one by one. In this model, there are two outlets, the producing MDM2. This is the equation for describing the first outlet. So T1 is the DNA turned on DNA. So it turned on made of alpha T, and it depends on the P53 because P53 activates the transcription of MDM2. And it deactivated with laid of beta T, and they transcript mRNA and it degraded and translated to MDM2 protein. And this protein can form a complex with a P53. So this term describes the forming complex between the P53 and MDM2. So the second mechanism repressing P53. And to describe the second outlet, we just switch the index from 1 to 2, and everything is same. And P53 can promote transcription of some Q, the promoting the degradation of P53. So this is the indirect repression with the bio MDM2. And P53 is regulated by these relations. They constantly transcript and they repress by MDM2 from the first allele and second allele by forming a complex by promoting degradation produced by P53. So by simulating this model, by performing the last algorithm, then due to the stochasticity, they can indeed observe the first skipping. The first line is the number of simulation or the cell, index of cell, and these different color describe the first skipping. Then in the experimental data, they shows the 91% first skipping, and simulation shows the similar frequency of first skipping. So it can produce the experimental data well, and in the oscillatory time series, they can really observe the first skipping. So to propose the role of these two outlets, they perform the simulation, knock down one of the outlets. So to knock down one of the outlets, they increase the degradation rate of mRNA from the second outlet 10 times. So as it decays fast, rapidly, there is no mRNA from the second outlet. So they developed the single outlet model, and they observed that in the single knockdown outlets, they shows the similar period with the controlled one, but as we can see, it shows the increased amplitude. So when one of outlet cannot lower the P53 cannot sustain the lowest oscillation. Amplitude is increased. So this is so we can conclude that a major influence of allelic buffering on P50 oscillatory on amplitude. So this is the model prediction. So they performed the real knockdown experiment. So experimentally, they knock down one of the outlet. This is the data. Then, as the model predicted, they show the increased amplitude in the single outlet knockdowns. So this experimental data support the biological modeling the model simulation prediction. And the next question is that does this amplitude specific effect on the molecular level influence to the cellular outcomes, cell cycle or cell cycle, killing cell cycle or sustaining cell cycle? So they observed the P21 level. The P21 is the protein, so regulating, determining, depending on its level, the cell determine whether they will stop the cell cycle or re-entry to the cell cycle. So as time goes, they measure the P21 in the controlled one and single allelic knockdown one. As time goes. Then they from the P21 level, they show the strong correlation in the amplitude of a P53 as the model predicted. And with the Gemini, with this, they detected which cell is the re-entry to the cell cycle. Then in the control one, they shows the low ratio of cell cycle re-entry. But in the single allelic knockdown case, as the P21 level increase, as P53 increase, they shows more ratio of cell cycle re-entry. So it means that allelic buffering mechanism really affect to the some cellular outcome, not only the molecular mechanism. And then finally, they check the sensitivity of the model. So they did sensitive analysis, and sensitive analysis is that. So we have a 14 parameter. For example, we will check the sensitivity of alpha p. Then we can perturb this parameter twice or 0.5. Then due to the stochasticity, if we simulate the 500 times with these three parameters, we can get the distribution of amplitude or the period. And then you measure the index S. S is defined as the, for example, let's we measure the amplitude of a leader. Then we can get an amplitude of increase from the increased parameter. And we can calculate the amplitude of original model and their difference, absolute difference. So large S means that it, as the parameter perturbed twice, the amplitude or the period changed significantly. So it is sensitive to the change of a parameter. So this index, how represent how weak the model against to the parameter perturbation. Then we can do this for all the 14 parameters and one allelic model and two allelic model, knockdown model and control model. And to seeing this 14 case, everything is so complex, so they averaged out the result with the 14 parameters. Then, as you can see, both of the amplitude and period, the two allelic model shows the low sensitivity to the perturbation to the parameter. It means that MDM to allelic buffering strengthens the robustness of a P53 oscillation via the mathematical modeling. And then they changed the three parameters, observed the oscillation by perturbing three parameters, and calculated the oscillatory region, where the transcriptional property such as amplitude and period is similar to the experiment. Then as we can see, unlike the knockdown model, the double allelic model shows the wide range of oscillatory region. And if you calculate the volume of oscillatory region, it is more wide. So MDM2 buffering broadly can expand the oscillatory region. So it supports to generate the robust regions under the existence of the noise. So they revealed the how allelic buffering mechanism have role under the presence of a noise. That's all for the listening. Any questions?
Can you explain one more time what is the meaning of oscillatory region?
Oscillatory region. So if we change the filter the parameters, the oscillatory properties change, such as period or amplitude. But in the P53 oscillate with the period of 4 hours, then it means that oscillating with for 20 hours is biologically implausible. So the biologically oscillatory region is that the region where the simulated the oscillation is similar to the experiment one.
And what is each axis?
Each axis is the parameter values over in model. So they just perturb 3 parameters. I think that to calculate the volume. Yeah.
Well, why two mechanisms are required for buffering?
Sorry, to what to cut?
Why two allelic mechanisms are required for buffering?
Buffer.
Is there any intuitive
Ah. Because during ambient pulse skipping, the MDM2 level very low. Then there is no repression to the P53. Then P53 can perturbate, but the other allele, the remaining allele suppress the P53 instead of the allele experiencing the pulse skipping. So that's why.
one allele is suppressed?
Yeah.
One
Yeah,
allele
the
is
other allele.
suppressed and
Yeah. So when both of allele experience the pulse skipping, they cannot block the increase of amplitude of P53.
so to to obtain constant.
Yeah. To sustain the lowest rhythms.
The buffering mechanism is the buffering mechanism related with network structure?
So
So, to my knowledge,
yeah.
the constant fixed point is, the buffering structure of constant fixed point is related with network structure.
Network structure.
But I don't know the buffering of oscillatory system is related with network structure. So is this a related network?
Okay. Expert of network in our like the Hyun Kim and Dr. Wang. Like that. Thank you. Other question? No question? Let's finish the